Welcome to Math Zone African Motives. Today, we're diving into the fascinating world of kinematics, the study of motion. We'll be working through question 1, covering topics like relative velocity and projectile motion. Let's get started. Our first goal for this session is to be able to calculate the relative velocity between two objects moving in different directions. This is a crucial skill for understanding how motion is perceived. Let's read the first question very carefully. A British Airways aeroplane. A leaves an airport and flies at a speed of 400 kilometers per hour due north. At the same time, another airplane B leaves the airport and flies at a velocity of 350 kilometers per hour s 45 degrees east. Calculate the velocity of airplane A relative to airplane B. First, let's understand what the question is asking. We need to find the velocity of plane A as seen by an observer on plane B. This is a classic relative velocity problem. The key formula for relative velocity is the velocity of A relative to B, which we write as v sub AB, is equal to the velocity of A minus the velocity of B. We'll be using this formula to solve the problem. Because velocities are vectors, we cannot subtract them like regular numbers. We must use vector subtraction, which is equivalent to vector addition. We can rewrite our formula as v sub AB equals the velocity of A plus the negative of the velocity of B. The negative of a vector is a vector of the same magnitude but pointing in the opposite direction. Let's first visualize the velocities involved. We'll start with aeroplane A. Aeroplane A flies at a speed of 400 km due north. We can represent this as a vector, which we'll call v sub A, with a magnitude of 400 km and a direction of 90 degrees. Now for aeroplane B. Aeroplane B flies at 350 km s 45 degrees east. This means the angle is measured 45 degrees towards the east from the south direction. This corresponds to an angle of 360 minus 135, or 225 degrees from the positive x-axis. Now remember our formula. VB equals VA plus TSHV. We have VA and VB, so we need to find VB. The negative of VB is a vector of the same magnitude, 350 km, but pointing in the exact opposite direction. So if VB is CS45E, then VB is N45 du. The direction from the positive x-axis would be 135 degrees. We can now use the law of cosines to find the magnitude of the resultant vector, VB. The law of cosines is a powerful tool for solving any triangle when you know two sides and the angle between them. The law of cosines states that for any triangle with sides A, BC, and angle theta, opposite side C squared equals A squared plus B squared minus 2AB cosine theta. Let's make sure we write this formula correctly. In our case, the two sides are the magnitudes of VA and psi VB. The angle between them is 135 degrees. This is not the angle the original memo uses, which is 135 degrees with respect to the horizontal. Let's recalculate the correct angle between the vectors VA and plot VB. VEA is at 90 degrees, and VB is at 135 degrees from the x-axis. The angle between them is 135 minus 90, which is 45 degrees. Therefore, in the triangle formed by these two vectors and the resultant, the angle theta is 45 degrees, not 35 degrees. It's very important to use the correct angle within the triangle you are solving. Let's now apply the law of cosines with theta equals 45 degrees. V sub AB squared equals 400 squared plus 350 squared minus 2 times 400 times 350 times the cosine of 45 degrees. Let's calculate that. 400 squared is 160,000, and 350 squared is 125. The product term is about 197.9. So V sub AB squared is 84,511.3. The magnitude of the relative velocity is the square root of this, which is approximately 290.708 kilometers per hour. Now let's find the direction. We can use the law of sines for this. We need to find the angle beta, the angle of our resultant vector from the north direction, which is the direction of VA. The law of sine says that sine B over side B equals sine AC over side C. Let's apply it. Rearranging the formula, we find that the sine of beta is approximately 0.852. Taking the inverse sine, beta is about 58.46 degrees. So our resultant vector is 58.46 degrees from north, towards the east. We can state this as n 58.46 degrees E. Let's compare this to the memo's answer. The memo gets 693.173 km/h and W 69.082 degrees N. Our answer is 209.708 km/h and N 58.46 degrees E. There is a clear difference in both magnitude and direction. Let's figure out what might have gone wrong in the memo's calculation. It seems the memo is calculating the velocity of A with respect to B, using the law of cosinus, but the diagram in the memo is actually adding VA and VB, not VA and VB. This is incorrect. The calculation also uses 135 degrees, which is the angle of VB relative to north or the x-axis, not the angle between VA and VB for addition. It's crucial to correctly identify the vectors and the angle between them. The correct answer for the velocity of aeroplane A relative to aeroplane B is 290.708 km per hour in the direction of north 58.46 degrees east. This means from the perspective of plane B, plane A is moving away at this speed and direction. Great work on the first problem. Our next goal is to solve a problem involving combined velocities, like a plane flying in the wind. We'll focus on calculating the resultant velocity when two vectors are perpendicular, and then we'll learn how a pilot can determine the heading to reach a desired destination. Let's read question 1.2 carefully. Question 1.2. The velocity of a Boeing 747 aeroplane in still conditions is 550 kilometers per hour. The pilot wants to fly directly west, but experiences a crosswind of 90 kilometers per hour from the south. Let's break down the given information. The velocity in still conditions is the velocity of the plane relative to the air, which we call the airspeed, or v sub p. This is 550 km/h. Next, the wind. The question states the crosswind is 90 km from the south. The key word is from. This means the wind is blowing towards the north. Let's call this the wind velocity, v sub w. It has a magnitude of 90 km/h and points north. The pilot's goal is to fly directly west. The velocity of the plane relative to the ground, the resultant velocity v sub g, must point straight west. The magnitude of this velocity is what we need to find in part 1.21. So our mission is to combine these three vectors. The wind, coming from the south and blowing north, will deflect the plane's path. To fly directly west, the pilot must point the plane slightly south of west to counteract the wind's effect. Let's find out how much. The vector equation that describes this is v sub g equals v sub p plus v sub w. The resulting ground velocity is the vector sum of the plane's airspeed and the wind velocity. Since we want v sub g to be exactly west, the north-south components of v sub p and v sub w must cancel each other out. This means the pilot must have a southward component to their airspeed. Let's draw this out. We have a vertical wind vector v sub w pointing north. We need a diagonal airspeed vector v sub p that points south of west to fight the wind. The horizontal component of v sub p will give us the ground velocity v sub g. As you can see, this arrangement forms a right-angled triangle. This is very helpful because we can now use the Pythagorean theorem to solve for the unknown side. In our diagram, the hypotenuse is the plane's airspeed v sub p with a magnitude of 550. One leg is the wind velocity v sub w with a magnitude of 90. The other leg is the resultant ground velocity v sub g, which is what we need to find in part 1.21. Now let's tackle part 1.2.1. Calculate the resulting velocity of the airplane. Using the Pythagorean theorem, a squared plus b squared equals c squared. We have v sub g squared plus v sub du squared equals v sub p squared. Solving for v sub g, we get that it is the square root of v sub p squared minus v sub u squared. Plugging in our values, v sub g equals the square root of 550 squared minus 90 squared. This simplifies to the square root of 294 through 400, which gives us approximately 542.5586 kilometers per hour. This is the speed at which the plane will move relative to the ground. The memo gets the same correct answer, which is great. The resulting ground velocity is 542.5586 kilometers per hour due west. Next, let's look at part 1.2.2. Calculate the direction of the flight to fly directly west. This is the heading the pilot must take. Looking at our right-angled triangle again, the angle theta that v sub p makes with the west direction is the angle we need to find. We can use basic trigonometry here. The side opposite theta is the wind velocity v sub w, which is 90. The adjacent side is the resulting ground velocity phi sub g, which is 542.586. The tangent of theta is the opposite side over the adjacent side. Calculating this gives us a tangent of approximately 0.158. Taking the inverse tangent, we find that theta is about 9.42 degrees. The memo gets 9.29 degrees, which is a small difference likely due to rounding. It then states the answer as W 9.29 degree S. Let's make sure our answer is written correctly. Our angle theta is 9.42 degrees south of the west direction, so the heading is west 942 degrees south. This makes sense. The pilot must angle the plane slightly south to counteract the northward wind. The memo also states an answer as S 80.71 degree BW. This is the same direction but measured from the south. 90 minus 9.29 is 80.71. Both notations are valid, but W 9.42 degree S is more intuitive given the pilot wants to fly west. Finally, let's solve part 1.23, the time taken to cover 720 kilometers. To calculate time, we use the basic formula from kinematics. Distance equals speed times time. It's often written as S equals Vt, or sometimes D equals RT. We know the distance the plane needs to cover, and thanks to our work in part 1.21, we know the plane's effective speed over the ground. The distance S is 720 kilometers. The speed V is the ground velocity we found, which is 542.586 kilometers per hour. We just need to solve for time, t. Rearranging the formula, time equals distance divided by speed. So, t equals 720 divided by 542.586. This gives us a time of approximately 1.327 hours. The memo has the same correct answer. Excellent. We have now fully answered all parts of question 1.2, covering relative velocity with a perpendicular wind. We successfully found the resultant ground speed, the heading the pilot needs to fly, and the time taken for the journey. Let's move on to our final question for today. Question 1.3. This problem is all about projectile motion. Our goal here is to learn how to break down the initial velocity of a projectile into its horizontal and vertical components. This is the first step in solving any projectile motion problem. Let's read the question. Question 1.3. A shell is fired with a muzzle velocity of 850 meters per second at 25 degrees to the horizontal. Calculate 1.3.1. The horizontal displacement or distance of the shell after 12 sounds 1.3.2, the height of the shell after 12 feet. The first and most critical step in projectile motion is to resolve the initial velocity into its horizontal and vertical components. This allows us to treat the horizontal and vertical motions independently. We have an initial muzzle velocity, which we'll call u, of 850 meters per second, fired at an angle alpha of 25 degrees above the horizontal. The horizontal component of the velocity is found using cosine because it's the adjacent side to the angle alpha. So, the horizontal velocity u sub x is u times the cosine of alpha. Plugging in the numbers, u sub x is 850 times the cosine of 25 degrees, which gives us approximately 770.525 meters per second. Similarly, the vertical component is found using sine because it's the side opposite the angle alpha. So, the vertical velocity u sub y is u times the sine of alpha. Plugging in the numbers, u sub y is 850 times the sine of 25 degrees, which gives us approximately 359.255 meters per second. Now that we have our components, we can answer the questions. First, part 1.3.1. Calculate the horizontal displacement or distance after 12 seconds. For horizontal motion, we assume no air resistance. This means the horizontal velocity is constant. We can use our familiar distance equals speed times time formula. Here, the distance, s sub x, is the horizontal velocity, u sub x, multiplied by the time, t. Using our calculated u sub x and the given time of 12 seconds, s sub x equals 770.525 times 12, which gives us 9246.3 meters. The question asks for the answer in kilometers. To convert, we divide by 1,000, so the horizontal displacement is 9.246 kilometers. Let's check the memo. The memo gives 9.2444 kilometers. This minor difference is due to rounding in the cosine calculation. Our more precise value gives 9.246 kilometers, which is the correct answer based on our component calculation. Now for the last part, 1.3.2. Calculate the height of the shell after 12 seconds. For vertical motion, we have gravity acting on the shell, causing it to accelerate downwards. The vertical acceleration, a sub y, is negative 9.8 meters per second squared. The initial vertical velocity u sub y is 359.255 meters per second. The formula for vertical displacement with constant acceleration is often called one of the Suvet equations. The formula is s sub y, the vertical displacement, equals the initial vertical velocity u sub y times time t, plus 1/2 of the vertical acceleration. A sub y times time squared. Let's make sure we write this formula exactly as it appears in the memo to compare. Plugging in our values, the height h equals 359.255 times 12, minus 9.8 divided by 2 times 12 squared. This calculates to 43.111.06 minus 705.6, which gives us a height of 36.0546 meters. Converting this to kilometers by dividing by 1,000, we get a height of 3.605 kilometers. The memo has a very similar answer, with the difference again being due to rounding. Based on our precise components, our answer is correct. And there you have it. We've now completed all the questions. We learned how to resolve a vector into its components and apply these components to calculate both the horizontal distance and vertical height of a projectile. This method is fundamental to solving any projectile motion problem. We've had a great session today with Math Zone African motives. We've mastered calculating relative velocity, navigating with crosswinds, and analyzing projectile motion by breaking it into components. The most important takeaway is the power of vector resolution and addition. By carefully drawing diagrams and applying the right formulas like the law of cosines, the law of sines, or the Pythagorean theorem, you can solve these complex-looking problems with confidence. Remember, practice is key. Keep working through problems to build your understanding. If you found this tutorial helpful, please like and subscribe to Math Zone African Motives for more step-by-step solutions and clear explanations. Thank you for watching.